Imagine that we have an arbitrary distribution function. So we have an x, and we'll just graph f of x. And of course, every distribution function looks the same, although its shape can be varied. But they all start off at 0 at the leftmost point, and so this is the value of f of x, which is by definition the probability that the random variable x is less than or equal to little x. Right? That's the definition of the distribution function. And so it goes from 0 at the leftmost endpoint all the way to 1. So this inverse distribution function, it works as follows. You generate a random number between 0 and 1. Let's call it r. And then you find the inverse of that. Where did that come from? And here it is. It came from this point, x1. Then you generate another uniformly distributed random variable, r2. Find its inverse. There's x2. And this is how this procedure works. That each x is the inverse of the associated r. Why? Because by definition, r is capital F of xj. In other words, basically you generate a variable between 0 and 1 and find out what value of the random variable produces that value in the distribution function. And it turns out that this procedure works in every probability function. It can be continuous, it can be discrete. Of course, when you have a distribution function that looks like a step function and has gaps, you have to be a little more careful about how you define the inverse. It's usually defined as the minimum x that has that value. And the answer, then this works. So this is a powerful and general procedure for generating randomly distributed variables from any probability function just by being able to generate uniformly distributed variables between 0 and 1, as long as you can find the inverses. And sometimes this can be done automatically as in Excel using built-in functions, and sometimes you can do this just by programming the probability distribution function and doing a search. So if with that as background, if we want to simulate exact log-normal stock prices, how would we do that? Well, we have from Chapter 18, the work we did there, we have a formula for stock prices at time t, given that they start off at value as 0. And this should now look quite familiar. We have a mean drift term. This is a real-world model of an alpha minus the dividend rate of delta with the half sigma squared adjustment times t. And then we have the risky part of the return, which is the sigma square root of t times a unit normal or a standard normal. So the way we can generate these stock prices is we need to generate normals. And as I just exemplified, we can generate a collection of a sampling of standard normal variables by first generating a sample of uniformly distributed variables and using the inverse function. So that's all built in Excel, and it's built in many software. So we can generate a random sampling of z's, and for each one of those z's, we plug into this formula, we get an associated stock price. And we therefore have now a random sampling of stock prices, and the stock prices we generate will have exactly the right distribution in theory. Obviously, there's sample error, but the more stock prices we generate with this procedure, the more and more the sample distribution will look like the exact log-normal distribution we aim to reproduce. So again, the idea is we need normal variables for the formula. we can generate those from uniform using the inverse distribution function. And that's how we get, excuse me, that's how we get the random sampling of stock prices. If we want to generate a random sampling of stock prices, not in the real world, but instead for option pricing applications, we use the typical procedure of replacing alpha, the real world total return, with R, the risk-neutral world total return. What if we wanted to generate a path, this idea of a random path? Instead of only generating the stock price at time capital T, we might imagine that stock prices, of course, started as 0, and you might say, well, we should have a model for determining how those stock prices evolved from their initial price as 0 to their ultimate price, ST, that we sampled in the prior slide. So this procedure allows you to perform the calculation in steps. And what we're doing is using the same formula we had a moment ago, but going from time 0 to time h, that's one step. Going from time h to time 2h, that's the second step. And we do this until we finally get the time nh, which should be the value at time t, because we broke up the interval from 0 to time t into n steps, each of size h. And we just now do, and you'll notice that to do this, we need n values. That's what I say here. We need n random normals, standard normals, to produce one path, because I need n different normals to give me the n prices going from time 0 to time t. So this is a way of, instead of just generating the ultimate price at time t, it allows us to generate intermediate prices from S0 to ST. Now, if I'm evaluating, and again, I can apply this in the real world with alpha or the risk-neutral world with R. If I'm pricing options, I want R, not alpha. If I'm pricing a plain vanilla call or a put, the prior slide gives me the right approach. I can generate just the stock prices at expiry. I don't really care about the stock prices before that. I can just generate the stock prices at expiry, plug them into my payoff function, and do the usual averaging and discounting. And I'm done. But what if I'm pricing an Asian option? If I'm pricing an Asian option, I need to know for the payoff function more than the value of the stock at expiry. I need to know the value of the stock along its path from time 0. So this procedure generates, in this case, if H were in weeks and capital T were a year, this would help us price an Asian option that averaged weekly prices, because then we would have 52 weekly prices and we could do an averaging.